Now this is going to be a lesson on the reciprocal trigonometric functions. When we first introduced the inverse trigonometric functions, we mentioned that the notation that gets used for them is a little bit ambiguous. Now the reason that this ambiguity exists at all is because we actually do allow this to work for pretty much any other number except -1. So when we write this, we do mean that cos squared x is the same thing as cos x all squared. Sine to the 4x is also sine x raised to the power of 4 as well. Even when we write 10 to the negative 3x, that does mean the same thing as 10x all to the power of negative 3. However, when we actually write this, we actually do not allow this to be true, and I'm actually going to demonstrate that to you as well. To show you this, I'm just going to choose some random value for x, and then I'm just going to type the left and the right in to a calculator. So for example, let's just pretend that x was equal to something like 0.5. Now for the left-hand side, we're just going to type the cos inverse of 0.5. And we'll evaluate the value with a calculator. I'll just set the calculator to radians. So we notice that this value is just 1.05. On the other hand, if we go ahead and take the reciprocal of the cosine of 0.5, we'll notice that its value is actually different. Now since this value is 1.14, it's clearly not the same as the 1.05 that we got before. This means that when we write cosine to the power of -1, we mean the inverse function and not the reciprocal. Now to convince yourself that this is obviously false, you just have to review how the inverse function actually works, which I covered in depth in another video. When you plug in a value over here, it's interpreted as an angle, and that can be as large as you like. The value you plug in over here, however, is interpreted as an x-coordinate, and that means it can only be between -1 and 1. So for example, if you plugged in 3 on this left-hand side, you'd get an error, which is your calculator's way of telling you that 3 is outside of the unit circle. If that doesn't make sense to you, then I strongly suggest that you watch the video on the inverse functions. Now in that video, we came up with a way to get around this problem by redefining the left and the right side of these functions. Now for the inverse functions, we introduced arccos, arcsine, and arctan. Now, instead of writing cos to the -1 of x, we write a cos of x. You might also see it written as arccos like this. But for brevity, I'll just keep writing a cos. Similarly, for sine inverse, we can also write this as arcsine, and for tan inverse, we can also write this as arctan. So now that we've renamed the inverse functions, we can also go ahead and rename the reciprocal functions as well. So here we're saying that the cosine of x to the power of -1 is just equal to sec of x. Similarly, the sine of x to the power of -1 is equal to the cosec of x. And tan of x to the power of -1 is just equal to the cotan of x, which we write as cot. Now I always used to forget which one was which, so an easy way to remember is to just look at the third letter of each of the functions. Since the third letter of sec is just c, you know that it pairs with cosine. Because the third letter of cosec is just s, it pairs with sine. And because the third letter of cot is just t, it pairs with tan. Now remember that all of this ambiguity just comes from the fact that the sine squared x is the same thing as sine of x all squared. If it were up to me, I would probably just not allow this, and then all of this ambiguity just disappears. We actually don't need these brackets over here because they aren't actually serving any purpose. Now despite the fact that this might actually simplify things a little bit, the simple fact is that everybody does use these symbols, and you probably should get used to using them yourself. Maybe in the future, people will adopt a notation that gets rid of this ambiguity. But for now, this ambiguity is here to stay, and you should be aware of it so you don't fall victim to it. Now to actually show you how these functions are used, I'll just go ahead and give you a very simple example. So the problem's pretty straightforward. If theta is an acute angle, and sine theta is equal to 3/5, what is sec theta, cosec theta, and cot theta equal to? Now to actually solve this problem, let's go ahead and just visualize it with a triangle. Because we know that the sine of theta is 3/5, then the opposite side divided by the hypotenuse is also 3 and 5. Now we can find this missing side over here by using Pythagoras' theorem. In the first step, we can go ahead and move the 3 to the other side. And then we can take the square root of both sides as well. Now 5 squared is just 25, 3 squared is 9, so this whole thing is 16, and the square root of 16 is just 4. Now we can just go ahead and replace m on the triangle. Now we know that sec of theta is just the reciprocal of the cosine of theta. By using SOHCAHTOA on this triangle, we can see that the cosine of theta is just 4 on 5. And we know that the reciprocal of 4 on 5 is just 5 on 4. Now, a quicker way you could have got to this answer is just by realizing that since the cosine theta is the adjacent over the hypotenuse, then the sec of theta would just be the hypotenuse divided by the adjacent. Now we know that the cosec of theta is just the reciprocal of sine theta. Now, by using the exact same reasoning, we can just say that the cosec of theta is equal to the hypotenuse divided by the opposite side. And finally, since the cotan of theta is just the reciprocal of tan, then we can say that the cotan of theta is the adjacent divided by the opposite this time. Now keep in mind that this only worked because theta is acute. If theta was not acute, then you'd have to actually repeat the process that we performed on sec. Now that we've introduced these reciprocal functions, I'd also like to help you visualize them on the unit circle. To begin with, I'll go ahead and draw a unit circle with cosine and sine already marked for some random angle. Now, for this triangle over here, the hypotenuse is 1 because it's on a unit circle. The x-coordinate is cosine and the y-coordinate is sine. We also came up with a really cool visual for tan, which is the gradient, by taking this side and expanding it out so that it was equal to 1. Then we ended up with a triangle over here, and this length over here was tan. Now you might not remember why this side over here was equal to the tan of theta. So just to remind you, I'll go ahead and refresh your memory. We must have scaled this triangle over here up to get to this triangle. This side over here was equal to the cosine of theta, and then afterwards it's equal to this number 1. Now that means in order to convert this smaller blue triangle into this larger yellow triangle, we're going to have to go ahead and divide all of the sides by this cosine of theta, because the cosine of theta divided by the cosine of theta equals 1. Now, since the sine of theta divided by the cosine theta is the same thing as the tan of theta, then this side over here must be equal to the tan of theta. However, we never really looked at this side over here. It turns out that if you divide 1 by the cosine of theta, you get none other than the sec of theta. So this goes ahead and shows you that this whole length over here is always going to equal the sec of theta. Now it turns out that there's another triangle just like this to help you visualize cot and cosec. The first thing I'm going to do is I'm going to rotate this triangle so that it's above the ray that's hitting the unit circle. Now since this shape is just a rectangle, we can also go ahead and move these labels to this top triangle. Now this time, instead of extending this triangle so that it hits the line at x equals 1, we're going to instead extend the triangle so that it hits the line at y equals 1 instead. Now this time we've obviously scaled the triangle up by a different amount. In this case we've taken sine theta to the number 1, so that means we have to divide all the sides by sine theta this time. Now remember, we're going to divide 1 by the sine of theta to get this side over here. And remember, 1 divided by the sine of theta is just the cosec of theta. And finally, if we divide this side over here by the sine of theta, we'll get this long side over here. But now we just need to be a little bit observant. We know that the tan of theta is just sine of theta divided by the cosine of theta. Here we have the cosine of theta divided by the sine of theta, which is the reciprocal of the tan of theta. And now you just have to remember that the reciprocal of tan theta is just the exact same thing as cot theta. And therefore, you can use these triangles to help you visualize all the trigonometric identities and their reciprocals. Now there is just one more thing that I want to show you about these reciprocal functions, and that's going to be their graphs, which I'll do on a new page. Now in order to be able to graph the reciprocal functions, you need to know the graphs of the original functions. So I'll go ahead and graph on the cosine, sine, and tan of theta. Now first we'll turn our attention to the cosine of theta. Now remember that the sec of theta is just the reciprocal of cosine theta. To actually help us graph the sec of theta, let's go ahead and draw a vertical line that starts at theta equals 0 and sweeps all the way to theta equals 2 pi. Now we already know that when theta equals 0, then the cosine of theta is just equal to 1. Now the reciprocal of 1 is just 1, so the sec of theta just gets a dot over here. However, things do become a little bit more interesting when we actually move the graph to the right by a little bit, so I'll go ahead and move this line to pi on 4. Now this time it's probably a good idea to get a calculator involved, to help us figure out what just happened. So first off, let's just go ahead and type in the cosine of pi on 4. So we can see that the value we're expecting is approximately 0.707. Now my graph isn't 100% accurate, but you can see that it is roughly at that place. Now remember, the graph of sec theta is just 1 divided by the cosine of theta, so we should try typing in 1 divided by the cosine of pi on 4. Now this shows us that we wanted the value of 1.414, and that's roughly where I've drawn it on the graph. Now this immediately shows you that when the cosine of theta goes down, the sec of theta will just keep going up. But then when the cosine of theta is equal to 0, what is the sec of theta going to equal? So when theta equals pi on 2, if you actually try typing in 1 on cosine pi on 2, your calculator is going to give you an error. And this immediately tells us that we actually have a vertical asymptote at pi on 2. Now we don't actually need the calculator anymore, and we'll just continue sweeping through the function. Notice that you're also going to get another vertical asymptote at 3 pi on 2 as well. And now this whole thing is the graph of sec theta. Now we're going to repeat the exact same process with the sine of theta. So let me go ahead and draw on the line and the tracer. This time we're going to note that the cosec of theta is the reciprocal of sine theta. Now as you can see, I haven't actually drawn on a point for the cosec of theta. That's because the sine of 0 is just 0. And 1 divided by 0 is just undefined, so I can't really draw it anywhere. And that just means that the cosec of theta has asymptotes as 0, pi, and 2 pi. Now we'll just go ahead and do the exact same sweep that we did for the sec of theta, and you'll be able to find the graph of the cosec of theta. And now this over here is 1 period of the cosec of theta. Now we're going to go ahead and repeat this exact same process for the cot of theta as well. Just keep in mind that the cot of theta is the reciprocal of tan theta. If we just go ahead and look at this graph directly, we notice that there are going to be asymptotes at 0, pi, and 2 pi. Now before we go ahead and trace out the whole function, there are actually some points that I need to point your attention to as well. Because the tan of pi on 2 is undefined, then the reciprocal of an undefined number should just be undefined, right? However, it's not really that simple. As the tan of theta gets larger and larger, we know that its reciprocal must get smaller and smaller. So as we do get closer to pi on 2, our value is going to get so close to 0 that it might as well be 0. However, a more convincing argument comes from the triangles that we drew earlier. Now on this triangle over here, we said that this length over here was equal to the cot of theta. I want you to imagine what would happen if we increased the value of theta over here until it hit pi on 2. As you can see, this distance will shrink to be exactly equal to 0. Now this actually shows you why in certain contexts, mathematicians actually define 1 divided by infinity to be 0. But in general, we don't usually do that. However, in this case, we do define the cot of pi on 2 to be exactly equal to 0. Now with that out of the way, let's go ahead and do the sweep and show you what the graph of cot theta looks like. And now this is the graph of the cotan of theta. Because it's a little bit hard to see, I'm going to fade out the tan of theta just a little bit as well. And now these three are the basic graphs of the reciprocal trigonometric functions. Now just like you do for the normal trigonometric functions, you might also want to transform these as well. To do that, you can just use the same box method that we showed in another lesson. And now with that, we've actually completed our discussion on the reciprocal trigonometric functions.